Yes, ma'am. You are audible.
Can you hear me now?
Yes, ma'am. You are audible.
Okay.
Okay, go ahead, Mega. Introduce yourself.
जी भाई. Good evening, everyone. I hope you all are doing well. First of all, I would like to thank all our participants for joining us today. Myself, Megha Pachori, volunteer at AMURoboclub, would like to welcome Dr. Hashima Hasan. She is an alumni of Aligarh Muslim University and currently she is working as a scientist at NASA. And also she has worked as a deputy program scientist in James Webb Space Development, James Webb Space Telescope. And today she is going to speak on the engineering and technological aspects of James Webb Space Telescope. And further, you guys can mention all your queries which you want to ask to ma'am in the chat box. We will address them in the end of the session. Thank you, ma'am, for joining us today. We're extremely delighted by your presence. Over to you, ma'am.
Okay. Well, it's morning here, so I will say good morning. And it's since evening there, good evening. And Assalamu alaikum. It's a real pleasure for me to talk to students at AMU, where I was a student myself many years ago in the physics department. And so how many students have joined today? And how many young ladies are there? And how many young men? Can you tell me?
Yes, ma'am. In total, I guess over 20 students have joined, and more will be joining soon.
Okay. Okay, so I'm really glad to see that there are at least some girls there, because when I was there in AMU, I only did my MSc there, not my undergraduate, and we were 3 girls in our class, and it was considered a big class. So I hope there are many more this year, now. So let's start with, let me share my screen. I have a
Hello, good evening, ma'am. My name is Faiz Akram, and I'm doing my research in Jamia Millia Islamia. Actually, I wanted to ask you that I'm actually, working on CubeSat. I've started working on CubeSat. So, what's your take about CubeSat, basically? Any suggestion or anything you want to guide me about this, please? Thank you.
So are you working on science experiments which you put on CubeSats, or are you actually working on the development of the CubeSat?
I'm actually working on the development of CubeSat. I also have startups, and so that's why actually I'm looking for a business opportunity in this for universities as well as for the companies also.
I see. That sounds like a very interesting field, because I think CubeSats are very up and coming means of certainly for doing science, and also probably for other technological uses. But so I think that's a good field to go into. My only concern is that with so many people being interested in CubeSats now, space is going to get very crowded. It's already getting crowded. So that's the only concern I have for the future of CubeSats. But otherwise, it certainly is a very up and coming field. But you need to be aware of that also, that that there is going to be a lot of international competition for space, for being able to, for access to space. Let's put it that way.
Yes,
Ma'am,
thank you, ma'am.
Yeah.
can you please share your journey from Aligarh Muslim University to NASA? I think it would be really helpful to all our participants.
Okay, so it has been quite a a winding course. So, as they say, कि कई घाट का पानी पिया है. So I actually came to Aligarh from Lucknow. I did my undergraduate in Lucknow University because I belong to Lucknow. And then I came to Aligarh for my master's in physics. And at that time, Professor Zulur Rahman Khan, who was in physics, convinced me that I should go for a PhD. So I started doing my MPhil there. And then one day I thought, why not apply to University of Oxford? So I sent in an application to University of Oxford, and one thing led to another. I got they accepted me, but I didn't have a scholarship. So Professor Rais Ahmad, who was the head of department, advised me to apply for a Commonwealth scholarship. So I did that. It was advertised by the government of India through the Ministry of Education. I applied for the scholarship. I got that scholarship and I went to Oxford. So I did my PhD there. And then I came back to India and I joined, I came to Aligarh and I talked to Professor Zillur Rahman, and he was, of course, very happy. And he said, just go do whatever you want because, you have this degree. And so I joined as a visiting scientist at the Tata Institute of Fundamental Research in Mumbai. It used to be called Bombay then. And after 2 years there, I got a lecturer's position at the University of Pune. And so in Pune. So I joined there and I started teaching there. And, then I was under a lot of pressure from the family to get married. And so that I got married and my new husband was in the United States. So I came here. He was in North Carolina. And at that time, the part of North Carolina he was in was, just a lot, tobacco fields and forests. There was really not too much development there. But there was this one area which they were developing as a research area. It's called Research Triangle Park. And so there were research facilities opening there. And that's where he was. The National Institutes of Health had a research lab that he was working in. He also had a PhD. He's also an Aligarhian. He had a PhD from Aligarh, and he was employed by the National Institute of Health at this environmental science lab. So I started looking around. There were 3 universities in that area, and I started doing postdoctoral work at Duke University in nuclear physics, because my degree was in nuclear physics. And after about a year and a half, my work permit came through, and I was able to apply for a fellowship with a U.S. National Science Academy fellowship at the U.S. Environmental Protection Agency in North Carolina, where we were. And I won that fellowship. And so I switched fields from nuclear physics to environmental science. And at that time, there was a lot of air pollution in Denver, Colorado. And in the winter, a big brown cloud would descend. Denver, Colorado is in a valley, and it's a beautiful place surrounded by mountains. And, it's the Rocky Mountain, the valley of the Rocky Mountains. And a brown cloud was settled down. And so the government was concerned, that there was a lot of visibility degradation caused by it, and they wanted to know what was causing it. So that's the research proposal I wrote, that I was going to study the visibility degradation in Denver, Colorado. And so my thought was that I've done physics, I know mathematics. This is just optics. It's studying physics and mathematics, and I'm a theorist. So I can, develop a theory for it and figure out how it it's doing it. So I worked on it and developed a model. Then I went with my colleagues. We had a mobile lab. So we took that lab from North Carolina to Colorado, and I collected, I got an instrument from University of Minnesota. We borrowed an instrument to collect the dirty air on filters at different diameters. And then we brought that back to North Carolina and had the filters analyzed in the X-ray crystallography lab. And then I was able to, with my model, we published a paper. I was able to pinpoint that most of the visibility degradation came from carbon exhaust of cars. So in those days, there wasn't that regulation on. There was a lot of there was leaded fuel being used, and so the petrol was leaded, and that caused a lot of carbon pollution. At that time, my first baby was also born, and that's an interesting story, because when I got pregnant, I called the National Academy and I asked them, what kind of maternity leave do you have? And this was 1982. And they said, well, this has never happened before. We don't. And that person at the end of the phone said, I'll call you back. And he called me back after 3 days, and he said, we had a meeting and we decided you don't have this. You're not sick, so you don't take sick leave. You take maternity, so you can take leave without pay. So I had only 2 weeks of leave, so I didn't take leave till the day before my baby was born, and then I took leave. And then when he was 3 months old, I came back to the US. I had leave from Pune University. So I joined Pune University again. My husband got a job in Bombay. And so then after a while, I moved to Bombay and joined the Bhabha Atomic Research Center. And so, it was a challenge. And then I had another baby. And then after 2 years, we decided to come back to the US because of the visa regulations. We had a green card and we had to come back. And I found myself in Baltimore, Maryland, where my husband got a job at Johns Hopkins. And then I looked around, and there was this new institute called Space Telescope Science Institute, which was going to be the science center for the Hubble Space Telescope. And so I looked around, and they said, we are looking for someone to write the optical simulation software for the Hubble Space Telescope. Can you do that? So I thought to myself, well, sure, I can do that. If I can do nuclear physics, I can write the optical simulation software. So I said, yeah, I can do that. So they hired me. So I switched fields again, and I wrote the optical simulation software for the Hubble and its science instruments. And then when it was launched in 1990, we discovered, and I don't know if many of you know this because all of you were not even born then, that the primary mirror of the Hubble Space Telescope is flawed. So the images that came down were blurred. They weren't the sharp images we were expecting. And so since I had written the software, it became my job to analyze those images and to characterize the error so that a fix could be made. So, for 2 years I did that and worked with the engineers, and then a fix was made, and which was sent in the first servicing mission, and then we had a perfectly working telescope. And then at that point, I thought I wanted to do something different. And there was a job advertised at NASA headquarters. They were looking for a visiting senior scientist to manage their programs in UV visible and gravitational astrophysics. So that's how I joined NASA headquarters. And then I just stayed on, managing different programs. So that's my story of how I got to NASA.
That was great.
So have you got our slides yet?
Yes, ma'am. Yes, ma'am. We are ready with the slides.
Okay, you want to share your screen?
Yes, ma'am. I will share the screen.
Okay. Okay, so let's start again. So let's go to the next slide. So as I mentioned earlier, we think of James Webb Space Telescope at NASA's infrared eyes on the universe. Next. It really is a technological wonder because, can we go to the next slide? Because it will enable humankind to unlock the mysteries of the formation of the early universe. And it really is a tribute to the ingenuity and creativity of the human mind. With a 6.5 meter primary mirror, which you see on the left, and it's folded back on the right, and it has 4 powerful science instruments. It has already started studying the first stars and galaxies, atmospheres of extrasolar planets, and it'll learn where elements that form life came from, and much, much more. Next. So we have 4 major science goals for James Webb, and that is to look at the end of dark ages. After the Big Bang, the universe went dark because it was just filled with plasma and the photons were scattering off and couldn't emerge. And so when the first light came, when the first stars started being born, and then they started assembling into galaxies. So how did that happen? That's the second goal. We want to learn more about how stars were born and how planets were born, not only around our star, but around other stars. And then we want to learn about planets around our own solar system. We can learn more about this and how life began. Next. So Webb specialization is in the infrared. All of you are scientists, so you will understand this spectrum over here. So as you can see, the visible part of the spectrum, which we can see from our eyes, is really very small. And the phenomenon in the universe span all the entire spectrum. So if we want to understand what's going on, we need to look at all parts of the spectrum. So the Hubble Space Telescope goes from the ultraviolet to a little bit of the near infrared, but James Webb will go from near infrared to the mid infrared, and the Spitzer Space Telescope had gone into a little bit into the far infrared. So next. So why do we want to look in the infrared? And the reason is that after the Big Bang, the universe started expanding. And as it started expanding, the stars, the light from the stars and galaxies started stretching because the space was expanding. And so this diagram demonstrates that the light which started in the stars as ultraviolet and blue has stretched out, because the universe is now like 13.5 billion years old. And so in that much time, that light, which left as blue or visible, is now reached in the ultraviolet. So if we want to see in the infrared. So if we want to see the first stars and galaxies, we have to look in the infrared. Next. So another advantage of infrared is that it will help Webb peer through and examine dust. So on the left-hand side, as a demonstration, there's an image of what are known as the pillars of creation of this nebula. And this is an image in the visible taken by the Hubble Space Telescope. And in the middle is a Hubble image in the near infrared. And you can see that in the visible image, these dust clouds hide the newly born stars, which you can see in the near infrared light, because infrared light can penetrate the dust because of its longer wavelength. And on the right-hand side is the mid-infrared, which are even longer wavelengths. And so you can, and that is taken by the Spitzer Space Telescope. And you can see the glowing dust in the mid-infrared light. So infrared helps you to see what is hidden in visible and ultraviolet. Next. So infrared will also help us find distant planets. That's because planets are cool compared to stars, and they emit infrared light, and the bright stars are dark in infrared. So the image on the right was taken by the Keck telescope in Hawaii. It's a ground-based telescope. And the bright light of the central star has been obscured by something called a coronagraph, and you're able to see 4 planets orbiting. And Webb will be able to see many more extrasolar planets and see them in greater detail. Next. So here is just a summary of what I just said, that will study the formation of first stars, which were created 13.6 billion old. It'll enable us to see the birthplaces of stars and study how planetary systems were formed, and it will observe the giant gas planets in our own solar system. And we'll be able to study their weather and climate and their moons. Next. So let's go into the technology of the telescope, which is what you are more interested in. Next. So this is a mission which is led by the Goddard Space Flight Center, NASA's center in Maryland. And it's an international collaboration with the European Space Agency and the Canadian Space Agency. And the prime contractor for building the telescope is a Northrop Grumman space system. And the instruments are a near-infrared camera provided by NASA, University of Arizona, and near-infrared spectrograph, which is provided by the European Space Agency. There's a mid-infrared instrument, which is a partner led by the Jet Propulsion Lab. It's a partnership between NASA and ESA, the European Space Agency. And there's the fine guidance sensor, near-infrared images slitless spectrograph, or NIRIS for short, provided by the Canadian Space Agency. So you can see that when you're doing something as challenging as the Webb telescope, you need to partner with other agencies. And the Science Operations Center is the Space Telescope Science Institute in Baltimore. So in short, there's a deployable infrared telescope with a 6.5 meter mirror, which is segmented. It's composed of hexagonal, 18 hexagonal segments which fold back onto themselves. And it was launched by an ESA-supplied Ariane 5 rocket, which is actually a French rocket. And it was sent into an orbit called L2, and we can talk about it a little later. Next. So this is a feat of engineering, and there were many new technologies invented for Webb, including new generation detectors and materials and so on. But I'll talk just about a couple of them. And one of them is, I would think, the two biggest, most challenging were the primary mirror and the sun shield. So I'll talk a little bit more about it as we go on. Next. So the most important part of a telescope is a mirror, because you can think of the mirror as a light bucket. The more light you collect, the more you will learn about the objects you're studying. If they are far away, then you can see fainter objects. If they're closer, then you can see them clearer because more light is reaching you. And so as a comparison to the telescopes we've already launched, you can see the Hubble mirrors was 2.5 meter and the Spitzer mirror was 0.85 meters. So the Webb mirror, which is 6.5 meter, is much bigger and much more powerful. Next. So the mirror is composed of 18 segments. It has 6 degrees of freedom, plus the radius of curvature adjustments. The mirrors are made of beryllium, and that's because the beryllium is very light, very strong, and it doesn't change shape too much with temperature. And that's really important for Webb because it has to operate at 40 degrees Kelvin. And the mirrors have been polished to be the correct shape when they're cold. Excuse me. So the mirror design, the primary is an elliptical mirror. Then there's a hyperbolic secondary mirror, and then a tertiary mirror. And the tertiary mirror is required to correct the off-axis aberrations, which are caused because the mirror is so large. And then there is a flat steering mirror, fine steering mirror, which is used to stabilize the images from the vibrations of the telescope. And this gives diffraction-limited imaging at about 2 microns. Okay, and on the right, you can see there are the images of the mirror in the ambient, and you can see when it is cold how smooth the images are. Next. So here's going to the fine steering where it's adjusted and then it's finally goes to the focal plane and the science instruments. On the right-hand side, on the top, you see the back of one of the hexagonal segments of the mirror. And this has, on each of the 6 corners of the segment and in the center, there are really little motors, and they help adjust the shape of the mirror. So there's 7 degrees of freedom. And in the bottom, there's a picture of a telescope emerging from a testing chamber at Johnson Space Center, where it was sent to test the optics of the telescope. Next. Can we go to the next slide? Can we go to the, yeah. So here's just a little bit more about the mirror, just showing you some pictures, just to give you an idea of how big more properties of the mirror. Next, and comparing it with the mirrors of the other telescopes. Next. So here, this is the mirror being prepared. You can see that the back plane of the mirror and each segment is being installed robotically in it. And this was done at Goddard Space Flight Center in Maryland. And so you can see one by one each each segment was put into place. And since you all are interested in robots, here's one place where robots were used to manufacture the telescope, to put the pieces together of all the 18 segments into the big 6.5 meter mirror. So here the last segment have been put and the mirror is ready. Next. So here's the mirror. It was in the viewing in front. I'm in front of the. That's me standing there at Goddard Space Flight Center. The mirror is in the clean room, and there's the viewing window where we were allowed to go and see the mirror from. And so you can see it was, once it was completed, there's this big, beautiful gold mirror over there, and it's coated with gold because it has to reflect infrared light, which is reflected by gold. So it's a very thin layer of gold. Next. So the other big technological challenge was the 5-layer sun shield, which has an SPF about 1 million. And this shield is about the size of a tennis court. It has 5 layers. It's made of heat resistance Kapton, which is a material which is, and it is very light, very thin. And it has been coated with silicon on the side of the sun shield, which faces the sun. And the other sides are coated by aluminum. And so this sun shield opens up like an umbrella under the telescope, and we need that to keep the telescope really cold, because since it's an infrared telescope, we don't want the signal from the celestial objects to be drowned by the heat of the telescope and its instruments. So we have to keep it really cold, and the sun shield keeps it cold, protected from the heat of the sun and the earth, so it won't get heated up. Next. So here is a time-elapsed movie where in Northrop Grumman, where the sun shield is being stretched to be tested. You can see they're pulling the sun shield on each side of the frame just to test the sun shield. So it was stretched fully, and all 5 layers were stretched, and to make sure that everything worked and didn't break. So you can see after stretching the whole thing, they're separating the 5 layers. So these were all the engineering challenges. So as I said, making the impossible look possible. So this was a test of the engineering model. Next. So why does the mirror have to be segmented? And the reason is it has to be deployed in a rocket which has a diameter of 5 meters. So to fit into the rocket, the engineers thought of this brilliant design that we can make it in pieces and then fold it up. So here in the middle, you can see the entire telescope is folded up, the primary mirror, the secondary, and everything. And that's how it was installed into the rocket and launched. Next. So here is showing where the different science instruments, what they are used to study different parts and different aspects of the celestial objects. So here the footprint of the science instruments are on these galaxies, showing what you can study with each instrument. So the cameras, there you can get images as well as spectra, and the spectrograph you can get spectra of thousands of galaxies, hundreds of galaxies at a time, and the mid-infrared you can get cooler objects. Next. So the near-infrared spectrum, you can study faint galaxies with an iris. You can study the composition of exoplanets' atmospheres, distant galaxies, and bright objects. With a NIRCam, you can study the earliest stars and galaxies, and mid-infrared, you can study cooler objects like debris disks around stars. Next. So this, I won't go through this, but for those who are interested, here are some of the science requirements and capabilities of the instruments. And again, this is where you engineers come in, helping the scientists, giving them the instruments they need. Next. Next. So here are just some images of the science instruments, of the camera, spectrograph, the mid-infrared camera, and the NIRIS instruments. Next. So here are some of the technologies which were actually demonstrated early on in 2006. And I'd like to mention the detectors, the near-infrared detectors, the mercury cadmium telluride, and the mid-infrared detector, which is doped silicon. These were developed specially for Webb. And then the micro-shutter arrays, which are like, and I'll show them later, they're like little windows. And then the wavefront sensing and control, as well as cryogenic structures. Next. So here the near-infrared spectrograph, this is the first multi-object spectrograph in space, which means you can see hundreds of galaxies at the same time, because on the right hand, this is a micro shutter, which has like little windows. You can open and close those windows depending on what objects you want to see at one time. So you can see many galaxies at the same time by choosing which windows you open. Next. So where is Webb's orbit? It's about 1 million miles away from the Earth at a point called L2. It's a Lagrange point, where it's a semi-stable point. So it's a good place to put a telescope because it stays relatively stable, and the telescope orbits L2, and with it orbits the sun as the Earth orbits the sun. So that's the point where the gravity of the Earth and the sun almost balance out. It's also far enough to keep the telescope cold, but close enough to the Earth so that it can communicate with it through the communication antenna and on Earth. Next. So this is, if you can click onto the movie, this is just showing how Webb unfolded in space. This is an animation that first, and then the sun shield is deployed. And first one side is deployed, then the other, then the 5 layers start separating out, and then the secondary mirror will get deployed after this. When they're all nice and tight, then the secondary mirror The secondary mirrors deployed, and then the primary mirrors deployed. And so that is the unfolding sequence of the telescope. Next. Can we go to the next slide? Yeah. So here, I think this is also a video showing the telescope launching from Kourou, which is in French Guiana in South America, and it launched on Christmas Day, December 25, 2021. It was a perfect launch, and it put Webb into really a perfect orbit, and so that it reached L2 with minimum fuel use. Next. Here's a picture of the actual Webb as it leaves the rocket. There's a camera on the rocket which took a picture of the Webb, and we heaved a sigh of relief when we saw this. Next. Next. So the commissioning process actually took 6 months. So after it had reached L2 and unfolded, it took 6 months to get it, to start taking the first images. It had to first cool down, then the mirrors had to be aligned, the instruments had to be calibrated, and then finally we started getting the first images in July of this year. Next. So this is, I've already shown this before, so let's go to the next one. So how were the mirrors aligned? So this is just, these are the actual images when the telescope was turned towards one object. These are the images which appeared in all the 16 mirrors. Next. Then the mirrors were adjusted so that this array started appearing in the order that it was required to. Next. Then each segment was then focused so that each segment came into fine focus. Next. Then all the images were stacked onto each other. So first, as you can see, each segment was focused, and then the segments were, so this was the alignment, and then the segments were again moved, so the images were stacked on top of each other to give one perfect image. This was the image stacking. Next. So here is the actual image from the telescope after the stacking was complete. Next. And this was the final evaluation image, which was released by NASA on 2nd of March. It's the image of a star. Next. And this was when Webb was getting ready for science, and all the instruments were focused, and this was the sharpness test released on April 28. And next. And then these were the first, which all of you, I'm sure, have seen. And then next. And we are releasing more and more images, and this is one of my favorites. That's why I put it there. This is an image of Jupiter, it's so clear and sharp. It's showing the auroras and hazes on Jupiter. So we are really, it's beginning to show its promise already in its earliest images. Next. So I just wanted to make you aware that anyone here, if there are any astronomers here who are interested in analyzing Webb data, it is all archived in the Mikulski Archive for Space Telescopes. Anyone can go, the data is public. Anyone can go and get the data, analyze it, and do your own analysis of the Webb data. Next. Yeah, so this is a nice website. It's if you want to learn more about it, or if you want your colleagues or people who know less about web can go into this website and learn about it. And next, I think it's again some more websites. Next. Okay, so that was my very quick overview. And I'm sorry I had to rush through it because we got late. So if there are any questions, I'm willing to stay on if anyone wants to ask questions.
Yes, ma'am. There are queries in the chat box. I think we can answer them. Ma'am, one would want to ask, could you tell us about the ISRO contribution in NASA's project?
There's a lot of background. I couldn't hear. Can I tell you what about NASA? Can you repeat?
Ma'am, the question is, could you tell us about ISRO contribution in NASA's project?
My contribution. Is that the question? I really can't understand the question.
Ma'am, the question is, could you please tell us about ISRO's contribution in NASA project? ISRO contribution.
Oh, ISRO. Oh, ISRO was not a partner in James Webb. ISRO is mainly partners in earth science. They have a lot of partnership in earth science. They also had some partnership in planetary science in the moon mission. But I don't think we've had any partnership in astrophysics with ISRO. It's mainly been with planetary or with Earth. Actually, there's quite a lot with Earth. And as I said, with planetary science.
Okay, ma'am. Next one, Farhan want to ask, why mirror shape is hexagonal?
Why is it hexagonal? So the engineers designed it so in a way that the mirrors could, once they were put together, they could be as close, the complete mirror could be as close to a circular mirror as possible. So they designed it after the mirror of the Keck telescope, which is in Hawaii. And those are two telescopes which are each 10 meters in diameter. And they are hexagonal telescopes. So the hexagons can fit into each other very nicely, as you can see from this image. And they can, there is the edge of the mirror is as close to circular as can be done. And also, the imaging, the reflections and the imaging are able, you can not simulate, but reproduce a perfect circular mirror.
Okay, ma'am. Ma'am, next question is, why does the sun shield have 5 layers rather than one thick layer?
That's a good question. I think the engineers figure out what would work best because the goal was to keep the telescope at 40 kilometers and also to have as simple a design as possible. So they didn't want too many layers, they didn't want too little. What was just right is, what they calculated and experimented with, and that's the number of layers they came up with.
Yes, ma'am. Ma'am, next is, what's next after James Webb Space Telescope?
It's the Roman telescope, which we are building. It is actually a 2.5 meter telescope like the Hubble, but it has a bigger field of view. It will also be infrared, and it will have visible as well. And it is largely a survey telescope. And its main goal is to study dark energy. So we are working on that, and it's scheduled now for launch around 2025, 2026.
Okay, ma'am. We are really looking forward to it. So next question is, ma'am, how images taken by James Webb Telescope is stored?
Is it sold?
Is stored. Where we store that image?
Oh, no, I don't understand. Sold? No, I don't hear very well, so you may have to repeat it. What do we do with the image?
Ma'am, the images which were taken by the telescope, where we store that image?
That is stored, yeah. As I said in one of my last slides, they're archived at Mikulski Archive for Space Telescopes. That's where they're archived. That's where they're stored. And those archives are open to the public. Anyone can go and get the data from there and analyze it. I mean, they analyze as data, not as the images, but yeah, that's where you get all the data.
Okay, ma'am. Ma'am, next is why James Webb is limited for 10 years, but Hubble telescope is for lifetime?
No, Hubble is not quite for lifetime, but James Webb is limited because it needs fuel to keep it in its orbit around L2. And so when the fuel gets exhausted, then that ends the lifetime of the telescope. Hubble orbits the Earth, and it will also, gravity is eventually going to pull it down also, so its lifetime will also end, but its actual lifetime will end when its instruments die, but its orbit is, determined by gravity around the Earth. It's orbiting the Earth. It's what we call a low Earth orbit. It's only about 300 miles from Earth.
Ma'am, the next one, ma'am, can you please tell a bit about how working culture of NASA is different from other space exploration agencies?
That's a difficult one. I am not familiar about working culture of other agencies. But I would expect that the others also work like us, that you aim to get the best. You have to make a judgment between the risks that you take, the costs. You have to balance costs and risks and schedule. And so I would think that most agencies would be doing that, but we don't know. I don't know the inner workings of the other agencies.
Okay, ma'am. I think we are done with our queries.
Someone is asking in chat if there are opportunities for mechanical engineering. Well, mechanical engineering, as you know, someone's mic is open. Mechanical engineering, as you know, is the workhorse engineering. It is needed for everything. So yes, mechanical engineering is definitely needed. I mean, who are the people who decided how the mirrors open and close and fold? I mean, it's the mechanical engineers who help design the sun shield moving up and down. And so I think mechanical engineers are required everywhere. They work with the other engineers to make things happen.
Okay, thank you.
So I hope I've given you all a little bit of an appetite for the exciting engineering that all of you can do. And if you can help scientists to make science happen, that's great. If you can use your engineering skills in other ways. But this is just a demonstration how, people think of things which would be impossible to do, but then they use their ingenuity to make them happen. And so I would like all of you to think big and to think not to be, not to be frightened by aiming big or trying challenging things, because that's the only way to go ahead and, as we say, go reach for the stars.